So stated before, we're going to be using the two-film theory in order to solve our gas absorption problems. Stated, we need two films. Hopefully you get the idea that the first film will be the gas and the second film will be the liquid ones. So we want to see the film-film interaction between gas and liquid. For this, we need to consider the interface between the gas phase and the liquid phase. So essentially what you want to make your analysis is this interface right here. So understand that there are bulk properties on both cases. Understand that there are two interactions area and there is one single two-phase contact right here. Let me clean this away. This interface can represent any point in the gas absorption equipment where the gas contacts the liquid. So later on we're going to see how absorption columns work, but essentially you can do this model as the example previously stated for the glass. You can do it from the top, the middle, maybe almost at the end, or even at the end. So the film interaction is the same. You have a liquid and you have a gas and there is one interaction point. So let's get more technical. The analysis is essentially on the bulk gas phase. You want to know the mole content of our solute in the gas phase. You want to know the mole content of the solute in the liquid phase, in the bulk phase right here. And one of the hardest parts are to get the equilibrium, or let's say interaction. I stands for interface concentration or molar concentration of each species. You know probably that, let's say, if the gas in gas absorption, what we want to do is gas phase to liquid phase. So what you're going to have here is a drop in concentration. If we were having desorption, which is the contrary, we will see that this is backwards. We have a very high liquid amount and the gas is increasing. Okay, so the analysis is made done in the diffusion of solute A from the gas phase to the liquid phase. This is absorption. You wanted to model desorption, this will be reversed, but essentially the idea is solute A is going to interact in gas phase and liquid phase. Some of the assumptions that we use in two-film theory is, first things first, steady state. So steady state means that the thin of film size is the same, the velocity is the same, maybe the density, viscosity, all the properties are the same. Concentrations at any point in the tower do not change with time. So, okay, I get the idea that maybe here the concentration at this point is X, Cx, and the concentration at this point will be Cy. So clearly Cx must be lower than Cy. That's true, but that's more relevant to the distance or the x-axis or y-axis, whatever axis you're using, versus position. What we're talking about here is that as time passes by, there is no change at all. Cx will remain Cx, and Cy will remain Cy, and Cx will be always lower than Cy. So there is no concept of time. As time passes by, the conditions are the same. We are also going to assume sharp boundary conditions, meaning that the interface between the gas phase and the liquid phase are, let's say, quote-unquote sharp, meaning that you can actually differ them very easily, which in real life is kind of hard to see that. It's like a bubble. It's kind of hard to see where the gas bubble is, and well, but what we are going to assume is that it's just a area of contact. Also, one of the important parts right here, we assume laminar flow. That is, the film exists at the interface on both sides of the interface in laminar flow, meaning that this guy and this guy right here are in laminar flow, and these are turbulent flow, turbulent flow. No need to make an analysis of the transition zone right here, because as stated before, that's what we want to avoid. We don't want to model this. We just want to know bulk properties, which are easy to get, and interface properties, which are not that easy to get, but still relatively easy to get. Now we talk about equilibrium. There is equilibrium, meaning that there is actually, let's say, an equilibrium between the gas phase and the solute, and the liquid phase and the solute as well. So they are in equilibrium. If there were no equilibrium, there will be no interaction at all. Now the resistance is negligible, or negligibly to the mass transfer, meaning that these guys right here can be associated to the equilibrium concentration. So this is one of the most important parts you need to know. This YAI, meaning the mole fraction of A, our solute, in this interface of the gas will be in equilibrium, with its molar fraction in the liquid side again. Now they don't necessarily need to be the same, but they are in equilibrium. So later on you will see that actually we can assume this as the equilibrium concentrations. And there is no chemical reaction. Well, I think that's extra, but still no chemical reactions. If you're wondering if there is chemical reaction, most likely you gotta check if there are reactions between the species, and if there are reactions between the species, you cannot use this model, or at least you cannot use this simplified version of the model.